is to get you there. We have seen the basic rules for constructing the orbitals. We're going to give you a couple of 3 guidelines, and then we're just going to play that game today. Lord willing, we finish it up for first part of class on Thursday, and we'll be done. We need to get a periodic table up on the board so you can see it. One for one typing the password today, that's good. And the computer is 1 for 1 at actually firing up. That's good. Again, the application of wave physics to bound particles. Fancy language. When we do high dollar math to try and figure out where the electrons are in an atom and what their characteristics are, we come up with physics that's called quantum mechanics, and it gives us a function, a mathematical function that describes the electron. And that function is characterized eventually by 4 quantum numbers. Okay, we've talked about these. Let's sketch them really quickly. Well, good. I've spoiled the nice clean board already, so there we go. So 4 quantum numbers describe each each element in an atom. Note, yeah, we'll fix that in a second. No 2 electrons on the same atom. Have the same set of 4 quantum numbers. The other way of saying that is every electron on an atom gets its own set. Nobody else can have it. I wish I could say these words and you could internalize them immediately and fully understand it, but here is what I would have you know, whether you understand it or not. The wave function, that mathematical function, fully describes the electron. Where it is, what energy it has, how much energy it's going to take to pull it off, how it's going to interact with its fellow electrons. All of that can be known, calculated from that wave function. So when I say this electron has these 4 quantum numbers, that is 1 electron on the atom and no other electron is exactly like it. That's what we're saying here. This statement here, the note, this is the Pauli exclusion principle. Once 1 electron has its 4 quantum numbers, everyone else is excluded from having that same set. Again, quickly. The first is N, the principal quantum number. N takes on values of 1, 2, 3, etc. Theoretically through infinity. Practically through 7. Because once we get to n equals 7, we've run out of the periodic table. And we don't really care from a practical, chemical standpoint what goes on beyond that. The theoretician, particularly the particle physicists, are anxious for that. But that's cool. The second is L, which is the angular momentum. By the way, yes, sorry. Energy level. I said it, I didn't write it. N is the energy level. L is the angular momentum, quantum number, and L takes on values of 0, 1. Sorry, hand is betraying me this morning. 0, 1, 2, 3, and maxes out at N minus 1. My hand will not write today. So I can't know what values of L I have until I know what value of N I'm dealing with. This gives me the energy sub-level. We'll talk briefly about that this morning. And the shape of the orbital. We really only care about the first 4 values, 0, 1, 2, and 3, which we label S, P, D, and F to make life easy. Once you practice it a while, it does actually make it easy. Because again, the periodic table is not going to take us beyond those values. The third is M sub L, which is the magnetic quantum number. Once we put a charged species in an orbit, it's going to generate a magnetic field. M sub L is 0, plus or minus 1, plus or minus 2, up to and including plus or minus L. So M is bounded by L, L is bounded by N is integer values. And then the last one that we just talked about and said, okay, this is there, is called the spin quantum number. By the way, my bad, I'm getting ahead of myself. The magnetic quantum number tells us the orientation in space of the orbital. The electron, same thing. So again, as we start to play this game, if n is 1 on the first level, the only value for L is 0. That means M sub L can only be 0. So that's 1, 0, 0. The electron either can spin up, plus 1/2, or spin down, minus 1/2. So there's 2 sets of quantum numbers in the first level. That means I can only put 2 electrons in the 1s orbital. There are 2 elements on the top row of the periodic table. So there's a 1-to-1 correspondence in between position on the table and how many electrons we have. We'll label everything before the day is done. On level 2, L can be 0 or L can be 1. The 0 case is just like 1s, except it's on the second level, so we call it 2s. 2, 0, 0 plus 1/2, 2, 0, 0 minus 1/2. Two sets of numbers, 2 electrons. That on the periodic table would correspond to lithium and beryllium. It's first electron and the beryllium, the second electron on the second level. So we're on the second level. L equals 0, now L equals 1. So if L is equal to 1, then M sub L can be minus 1, 0, or plus 1. So there's 3 L values, minus 1, 0, plus 1, by our rules. L is 1, minus 1, 0, plus 1. Each one of those, plus or minus 1/2, plus or minus 1/2, plus or minus 1/2. So 3 times 2 are 6. So there are 6 sets in this 2p sublevel. So on the first level, there's 2 electrons. On the second level, there's 2 plus 6, which is 8 electrons. We'll play this one more level down. So 3. And again, you'll notice that looks just like it did for 2 or just like it did for 1. It's just we're on a different level. So this is going to be 3s, 2 sets of quantum numbers. If n is equal to 3, then L can also be 1. And M sub L can be minus 1, 0, or plus 1. And M sub S is always plus or minus 1/2. So again, still 6 sets. That looks just like 2p, but it's on the third level, so we call it 3p. The last possibility is that n is equal to 3 and L is equal to 2. So M sub L can be minus 2, minus 1, 0, plus 1, or plus 2. From minus L to plus L. Plus or minus L, etc. So plus or minus 0, plus or minus 1, plus or minus 2, which is L. Each one of those can be plus or minus 1/2 on the M sub S. Which is 10 sets of quantum numbers. So n equals 3, 2 plus 6 plus 10 equals 18 electrons. Can be housed in the third level, and this is SP D. I'm getting all head up. My glasses are starting to fog. If we go to the fourth level, 4S, 4P, 4D, 4F. 2, 6, 10, 14. By the way, that's 2 times 1, 3, 5, 7. So it's just how many orbitals? Odd numbers, 1, 3, 5, 7. Multiply by 2 because each orbital can house 2 electrons, one spinning up, one spinning down. So that means 2, 6, 10, 14. So there's 18 electrons. We can play this game on out. Here is all of this in one simple table, in one straightforward table. If it's not simple, at least it's straightforward. If n is equal to 1, the only value of L is 0, that's 1s. And level 2, you have 2s and 2p. On level 3, you have 3s, 3p, and 3d. On level 4, you have 4s, 4p, 4d, and 4f. On the periodic table, we get to level 5, 5s, 5p, 5d, 5f. The fifth level has a fifth sublevel. It's 5g, but we don't have elements that have that many electrons. So let's not worry about it. You know it's there, but it's not there. You know it's there, it's not there. It's right in our head. 6s, 6p, 6d, and again, there exists 6f, 6g, 6h, but in the real world of chemicals, real world of elements, we don't need those orbitals. We don't have electrons to fill them. As a matter of fact, if you believe one of my students from about 5 years ago, they're impossible. You got electrons traveling faster than the speed of light, or spontaneously being destroyed and created. It's really fun. 7, 7s, 7p, D, F, G, H, and J. The set you got there is all of the ones that are filled on the periodic table. L is equal to 0. That's an s orbital, holds 2 electrons. L is equal to 1 is a p sublevel, holds 6 electrons in 3 orbitals. L is equal to 2 is a d sublevel, holds 10 electrons in 5 orbitals. 5 spinning up, 5 spinning down. L is equal to 3 is an f orbital, holds 14 electrons in 7 orbitals. Whoops, I have one too many there. Let's just do that. That'll make life so much easier. That's helium. This is the S block. This is N equals 1, 2, 3, 4, 5, 6, 7. So hydrogen has 1 electron. Where is it? Well, where is it in the table? It's in first row in the S block, so it must be a 1s orbital. It's on the first row. What's the only thing that's there on the first level? S. So that's 1s. Here's lithium. Its third electron, its last electron then must be in a 2s orbital, because here it is on that position in the table. I'm presupposing something, you're just accepting it because I haven't given it to you yet, so here we go. There is the Pauli exclusion principle. So no two electrons can have the same set of 4 quantum numbers. There is also what is called the Aufbau principle. If we were German, our life would be easier here for just a minute. The Aufbau principle says this: orbitals fill from low energy to high energy. Didn't make that wide enough. It's like throwing rocks down a hole. Where's the first rock go? All the way to the bottom. Where's the next rock go? All the way to the bottom if there's space for it next to the first one. Okay, so now the first level is filled. Where's the third rock got to go? On top of the first two. That's all this is saying. We just throw them down the deepest hole, the lowest energy, and then fill up after that. And I don't remember whether it's chapter 7 or chapter 8. You can always hit the index. In Tro will talk about penetration. It simply says that when we get to higher levels, orbitals start to expand closer to the nucleus. And the closer they are to the nucleus, the lower their energy. And so a 2p sublevel is slightly higher in energy than a 2s because the 2s penetrates a little bit. 3s, 3p, 3d. Here's the bottom line for you. As n goes up, energy goes up. Higher n, higher energy, because that's what n's all about, is energy. As L increases, the energy goes up slightly. It's the energy sublevel. So here's 1, here's 2. Okay, so there's a 1s, and here's 1s and 1p. And 2p is slightly higher than 2s because L is bigger. Here's level 3, 3s, 3p, 3d. Here's level 4, s, p, d, f. Now, because of penetration, things happen. And we're going to have to remember this one of two ways. I'm going to show it to you graphically, and then I'm going to go to my go-to, which is the periodic table, because you always have a periodic table in front of you. Okay? Here is level 1, 1s. That's the only thing that's there. Here is level 2. It sits above, higher energy. Here's 2s, 2p. Here is level 3. Sits above level 2, 3s, 3p, 3d. Carefully, please everyone look. Here is level 4. Level 4, we are such that the 4s orbital actually fills up before 3d. 4s penetrates closer to the nucleus, so it has lower energy. So there's a crossover, 4s, 4p, 4d, 4f. That's level 4. There's one crossover with 3. Here's level 5. So here was 3s, 4s, and then 3d. So here is 3p, and then 5s, and then 4d, and then 5p, and then 4f. You're going, okay, how do I remember the crossover? Okay. 1 and 2 don't cross over. 2 and 3 don't cross over. 3 crosses over once with 4. 4 crosses over twice with 5. And if we had enough orbitals, 6 would cross over 3 times with 5. And you're going, too confusing. Show me an easier way. 2 ways. Different color ink here real quickly. If you take this form of the table and you just make diagonal lines, you get the filling up order. Five S, 5S, 4D, 5P, 6S, pardon me, 6S, and then finally 4F, 5D, 6P, 7S. I hope you're looking at me going, he keeps referring back to that table like he hasn't memorized it. I keep referring back to that table because I've never memorized it. I can reproduce the table, but better than that, I've got the periodic table, and when I show you something in a minute, you don't need this either. It's just some of you already know this much, and I'm refreshing your memory because it's a tool you've already known. 7S, 5F, 6D, and 7P. That's the specific filling up order. So the 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, 6, 2, 14. D is 10, P is 6, S is 2, P is 6, D is 10, P is 4. Pardon me, where did I? That's F. Here we go. I knew there was a 14 in there I'd missed. I'm going, okay. 1S, 2S, 3S, 4S, 5S, 6S, 7S, 2P, 3P, 4P, 5P, 6P, 7P. That's easy. Hey, what row am I on? Row 3. Where am I? I'm over here. If I know that this is the P block, then I'm filling up 3P orbitals. This is the D block. Where's the first D we see? 3D. So this is 3D. Hey, that's that crossover, that penetration. 4D, 5D, 6D. This is the F block. The first one of those is 4F and 5F. That's it. This gives us the filling up order. Okay, so 1S, 2S, 2P, 3S, 3P, next row, 4S, 3D, 4P, next row, 5S, 4D, 5P. The only thing you need to know in the periodic table tells you is that we jump down here when we get right here. So there is 6S, and then for F, we come back to 3, 4, 5D, 6P, and we go again. This periodic table is so nice that if you were to get up and look at it during the exam, it's got all of the electron configurations on there. It tells you, hey, these are the orbitals, and this is where its electrons are. It's a very useful periodic table. Again, for those of you who are not going to be taking the exam with us in person, I'm going to I will simply take a picture of that periodic table and post online as well. Okay? But if you do this a couple 100,000 times, it's easy. So I'll start with that statement. If you can remember this, S, P, D, and F. If you can remember 4 things. Here's the periodic table. Where's my black pen? I hope this is the one I was using. Looks like it. S, P, D, F. This starts with 1S, this starts with 2P, this starts with 3D, this starts with 4F. If you can remember S, P, D, and F, then you can tell me electron configurations all day long. How many electrons will fit in a 2s? Pardon me, how many electrons will fit in any s orbital? Well, how wide is that block? It's 2 columns wide, must be 2 electrons. How many fit in a d sublevel? Well, it's 6 columns wide, you can count, must be 6. How many in the d? So this is 2, 6, 10, 14. And you can count. This periodic table, the paper one on the wall, again, is more better because it shows you that break between lanthanum and cerium. I think that's cerium. I know it's actinium and thorium on 5F. And then you can count. It's 14 elements from cerium through lutetium, or 14 elements from thorium to lawrencium. The other blocks are easier to count. 2 on the left, S. 6 on the right is P. 10 in the middle is D. The transition metals, as we transition from the S block to the P block. We refer to these then as main block, transition, and inner transition because it goes here in the middle. I don't know if any of you have ever seen a periodic table where it's 2 and then 2 and then 14 and then 10 and then 6 on the far side. It takes a page and a half. They're just showing you that where they've stuck those 2 bottom rows where they belong. Why don't we do it that way all the time? Because that fits on 1 page. I had one textbook that had the front fly sheet that folded out and you had a full periodic table. It was my favorite one till it tore. Then it was not my favorite anymore. Pardon the poem. So here's what we're going to do. We're going to write, quote unquote, full electron configuration and orbital diagrams for the first 10 elements, and then we're going to pick and choose a half a dozen others and teach you how to play the game that I need you to be able to do from now until you are not doing chemistry. For some of you, that's Thursday of next week, but for most of you, it's going to be a while longer, like, I don't know, 60, 70 years. God blesses you with that many. So here we go. Okay, the first 10 elements have how many electrons or protons in the nucleus? Remember, we define the element based on how many protons it has, but a neutral atom has the same number of electrons. So we can just count the number. So that's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So there's the first 10 elements on the periodic table. That happens to be the first 2 rows. My lowest energy orbital is 1s. And hydrogen has 1 electron. So its electron configuration is 1s1. This tells me 1 electron in a 1s orbital. I'm not going to leave this up there. I'm going to move it over here. We label our orbitals. I don't know if I ever said this explicitly. We label our orbitals in L. So 1s. 1 tells me I'm on the first level. S tells me that L is equal to 0. That's my sublevel. Helium has 2 electrons. They will both fit in a 1s orbital. So its electron configuration is 1s2. To the uninitiated, we'd go 1s3, but we can't go 1s3 because an s will only hold 2 electrons. That's 1, 0, 0 plus 1/2, 1, 0, 0 minus 1/2. We don't need to write all that out. We just need to remember that s holds 2. We need to know why eventually, but that's fine. So there's lithium. So it has everything helium's got. Where's the third one go? 2s1. Yardstick. S1. Here's lithium. I'm walking the screens over. Here's lithium. Where is it? Second row. What block's it in? The S block. What column? 1. So second row, S block, first column. Second row, S block, first column. So the electron configuration tells me, we get that information from where it is on the table, or it tells me where it is on the table, one way or the other. How many electrons total? 2 plus 1, 3 electrons. 2 in 1s, 1 in 2s. Here's beryllium. 1s2, 2s2. Where is it? Second row, S column, second block. Pardon me, S block, second column. 2s2. 2 electrons in the first level, 2 electrons in the second level. 2s is now filled, so we jump over the break to boron. 1s2, 2s2, 2p1. Because S is filled. What's the next one? Well, there's boron. Where is it? Second row, P block, first column. Second row, P block, first column. 2p1. My guess is you can fill out the rest of the table on your own now. 1s2, 2s2, everything that it had before, now it's 2p2. Nitrogen, 2p3. Oxygen, 2p4. Fluorine, 2p5. And finally, neon. which is 2p6. Again, there's neon, far right hand into the column. What seems like either 2 days or 2 years ago, when we first started talking about chemistry, we said the noble gases have got something going on that makes them inherently stable. Then we started arguing it's electrons that allow atoms to interact. So now with quantum mechanics, our final argument is that the noble gas is neon. Helium before it, neon here, are happy because they are at the end of the row, so their levels / sublevels are filled. And if we do the math, that energetically is low. It's a low energy situation. So what is nature doing? What nature does, it rolls downhill. Balls roll down the hill. Why? So they have less energy. I offer you a chair, what do? Sit down. So you have lower energy. I remark, the chair reclines. What do? You recline. So you have less energy. I turn off the lights. What do? You go to sleep. Okay? You know how you get an old man to fall asleep in a chair? Give him a chair. It's real. So that's all that's going on there. Now, let me show this to you graphically in what is called an orbital diagram. And you will see this either using boxes or just dashes. Mrs. Rogers uses a great example of an apartment. She's saying, okay, a 1S apartment has 2 beds. So there's 1S1. The box tells me there's 1 orbital. The arrow in this case tells me that it's plus 1/2. Could I have written it with the arrow down? Sure. Doesn't matter. If there's only 1 electron, it doesn't matter whether it's up or down. It is up or down. Pick one. I am generally a positive person, and I'm trained. You're right. The first one points up. Okay. Here's helium. 1s. 1 spinning up, 1 spinning down. Hey, they're in the same orbital, so they have the same N, the same L, the same M sub L. What's the difference? 1 is M sub S plus 1/2, spins up. 1 is M sub S minus 1/2, spins down. That's illegal, because that tells me that I've got 2 electrons with the exact set of 4 quantum numbers. That means I have 2 electrons that are identical. They're in the same space at the same time. Can't happen. Physically impossible, and therefore must be theoretically impossible as well. The Pauli exclusion principle says this can't happen. This is a violation of the Pauli exclusion principle. Pauli says no can do. I can't go for that. Y'all don't know that 70s song, but I do. Oh, you do? Good for you, Ryan. Your parents raised you well. All right.
I just got a CD the other day.
Oh, that's Hall & Oates, right?
Yeah.
Sorry. Not sorry. Okay. So here is lithium. 1s2, 2s1. Here's beryllium, 1s2, 2s2. Nothing new here, we're just going to the second level. And again, I would argue this information right here, this is your new best bud if we're doing electron configurations. So there's lithium, there's beryllium. Where is it? Second row, S block, second column. So 2s2, that's its last electron, 2s2. It's got 4 electrons. Where are the other 2? What was the orbital before it? 1s. Okay, so 1s2, 2s2. Remember, the Aufbau principle says we're going to fill them up in order. So beryllium's got 4 electrons, so the first 2 go in 1s, the next 2 go in the next available orbital, 2s. So in this strangely built apartment building, there's a 2 bedroom, you want share a room. There's a 2-bedroom apartment here, a 2-bedroom apartment here. Here's a family unit with 6. That's where we're going next. So here is boron. I'm going to drag it over here where I've got some space. We'll alternate back and forth now. Sorry, we're erasing the important information, but you already had it down. So there's 1s, 2s. Watch carefully. There's 2p. P means that L is equal to 1, which means there's 3 rooms. M sub L minus 1, M sub L 0, M sub L plus 1. We're back still at that information on the far left. 1s2, 2s2, 2p1. Put 1 arrow in 1 box pointing in 1 direction. Because I grew up in the West where we write from left to right, and because I was trained that the first electron points up just to make things consistent, I'm going to put it there. Could you put it pointing down in the middle box if you're of a mind, just as long as you only put 1 in 1 box, because I've only got 1 electron to put there. Here is the next critical bit. Here is carbon. Here is carbon. 1s2, 2s2, 2p2. And here is the last bit of information we need to know when doing these. When I'm filling quote-unquote degenerate orbitals, when I'm filling orbitals in the same sub-level, when I'm placing electrons in the same sub-level, everybody gets 1 before anybody gets 2. There are 2 people living in a 3-bedroom apartment. Unless they're married, one's going to be in one room and one's going to be in the other one. Right? Why? Because that's just going to be better. This is called Hund's rule. And yes, you're thinking, how does he say Hunt when it's a D? Because he's German. Hund's rule, to be really exact, but Hund's rule. When filling orbitals of equal energy, each is half filled before any is fully filled, and the spins are aligned. That means I put the second arrow in a second box and make sure they're pointing the same direction. That gives me the lowest energy situation. It's lower energy because I'm not forcing the electrons to share a room. It's lower energy because they're both pointing the same direction, which means their magnetic fields are aligned. So that's going to make the lowest energy situation. This is Hund's rule. In English, everybody gets 1 before anybody gets 2. If I'm in a sublevel, 2p, there's 3 orbitals. What do? Everybody gets 1 before anybody gets 2. And everybody faces the same direction. So here is nitrogen, 1s, 2s, 2p. It's 1s2, up, down. It's 2s2, up, down. It's 3p3, 1, 2, 3. Everybody got 1, nobody got 2. Everybody's facing the same direction. That's Hund's rule. We're going to come back to nitrogen in just a second and show you what you can't do. It's important to know how to do it, but it's also important how to recognize when someone's done it wrong. Here's 2p4, oxygen. 1s2, up and down. 2s2, up and down. 2p4. Again, I'm going to wait till pencils are down so you can watch me do this. Just become just as retentive about this as I am, and you'll get it right every time, okay? I've been doing this for 45 plus years, and I still do it the same way every time. 2p4, 1, 2, 3, 4. I count them out, usually out loud if there's no one in the room, or definitely out loud when there are somebody in the room. Okay, 1, 2, 3, okay, come back, and now I get 4. I could have put the fourth one in any box as long as it's spinning down. Pick one. I start at the left every time. So that means that fluorine, 1s, 2s, 2p. 1s2, up, down. 2s2, up, down. 2p5, 1, 2, 3, 4, 5. By the way, how many empty rooms, how many empty beds are there in fluorine's apartment? 1. How many bonds is fluorine going to make then? 1. Why does it want to make one bond? So it can fill all of its beds and be happy, just like neon. Hey, hang on, here we go. Neon, 1s, 2s, 2p, up, down, 1, 2, 3, 4, 5, 6, up, down, down, down. There's neon, 1s2, 2s2, 2p6. Why would neon want another electron? It'd have to build a whole nother floor just to house one electron. Never going to happen. Why would it want to give up an electron? Well, everybody is nicely paired. They've got a roommate they like. Leave us alone. That's what neon's saying electronically. And quantum mechanics backs us up on that. It's our experience. We know that's what neon does. Neon no react. It's an inert gas. Okay, now we have a theoretical reason why. Come back up here to helium really quickly. Helium has a 1s2 configuration. So that means in any of these, I've just done it for neon, but in any of these, I can replace 1s2 with just bracket helium. That means it's got those electrons plus these extra. This is called the noble gas core. And this is the valence configuration. I'm about 99.5% sure that I did my 5-minute lecture on the word valence coming from quantivalent, the Brits. Yes? No? You've slept since then and had turkey. So, valence simply means attraction. These are the electrons it uses to attract things with. By the way, it's p6. Its electrons, all of its electrons in its outer shell are paired up, so it's not interested in attracting anybody. Here is the valence configuration for neon. There's the valence electrons for neon. It's got one room left. It's got one bed left in that bedroom. This is the neon core. So if we wanted to expand this, let's look at sodium. How many electrons does sodium have? 11. So element number 11 has 11 electrons, okay? Where is it in the periodic table? It's in the third row. It's in the S block. It's in the first column. Its last electron is where? 3s. What comes before 3s? Well, 2s and 2p. What comes before 2s? 1s. These are filled. 2, 2, and 6. 2 plus 2 plus 6 make 10, plus 1 equals 11. That takes a while to write out. Hey, let's do this instead. Neon 3s1. So it has the quote unquote the neon core. Its valence 3s1. So how many electrons does neon have that it can actually use to do chemistry? 1. What's the most common thing that sodium does with its 1 electron? What do you know about sodium? It tends to just give it up. It says, I don't want this electron. It gives it up, becomes sodium plus. This is just like a union shop, last in, first out. What's the last orbital we filled? 3s. Pardon me. What's the last orbital we put an electron in? 3s. Where's the first electron we take it out? 3s. Again, if it loses that, hey, what's left? The neon core. Oh, the neon core. Neon's really stable because all of its orbitals, all of its sublevels are filled. So what is sodium doing? Why does sodium form a +1 cation? So its orbitals can be filled. It can achieve electronic nirvana. Okay? As we mix cultures. So for giggles, let's write the electron configuration for chlorine. How many electrons does chlorine have? 17. Where's chlorine? What row? Third row. What block? P block. What column of the P block? 5. So that means its last filling sublevel is 3p, and it's got an occupancy of 5. Again, there it is on the third row. Just count over aluminum, silicon, phosphorus, sulfur, chlorine. So 3p5. What comes before that? Well, if I hadn't erased our really useful table, we'd say, okay, well, sodium and magnesium are filling 3s, so that's 3s2. What's before that? 2p, which holds 6. What's before that? 2s, which holds 2. And at the bottom is 1s, which holds 2. Look, 2, 4, 10, 12, 5 makes 17. The crowd goes wild. It has the neon core. It has a valence of 3s2, 3p5. Three S2, 3p, 1, 2, 3, 4, 5. How many beds left open? 1. Hey, by the way, look at this. There's fluorine. Valence, 2s2, 2p5. Here's chlorine, 3s2, 3p5. What does fluorine do every time? Grab an electron, become F minus. What's the most common thing for chlorine to do? Grab one electron, become Cl minus. Why do they behave similarly? Why is the periodic table the way it is now? Quantum mechanics says they have similar or parallel electron configurations, so they're going to behave similarly. Guess what happens if we jump down to bromine? It's going to be 4s2, 4p5. Iodine, 5s2, 5p5. They're going to look just the same on the valence aspect. Okay, so we're not surprised then that they have similar chemical activities because electronically they're built the same. The game that we just played works perfectly as long as I stay in the S block or the P block. There are some weird things that go on when we get into D and F. We're going to play this game 2 or 3 more times in the S or the P block. When we start class on Thursday, we're going to look at just the first row of the D block, 3D. We're going to step through that quickly. And then there's a couple of other things we want to talk about. Okay? So bear with me. Let's do another few examples of these. I'm going to resketch. Oh, here it is. It's not all completely erased. I'm going to resketch it more betterish. Here is our good friend, the helpful periodic table, which we remember just in block form. S, P. I always put hydrogen and helium explicitly so we can see where they are. D, F. 1s, 2p, 3d, 4f. I learned to do this my second semester in college, and then every time anyone handed me a periodic table on an exam after that, I just wrote that information down until I didn't have to do it anymore because I knew it. Just throw those numbers down, then you're good. Okay? There's 2 rows here. Here we go. Et cetera, et cetera. So now let's come all the way back over here so that the people online can't look at both ends at the same time. I'll go back and forth. You'll be okay. Hey, let's not get ugly yet. Let's do arsenic. Arsenic has how many electrons? 33. How do we know that? Because it's element number 33. The periodic table told me. That's how I know it. I couldn't have told you that off the top of my head. If I thought a minute, I know that bromine's got 35, and I could have backed up. That's just a number that stuck. But it's much easier for me not to memorize it, to just go AS 33. Okay? Now, let's build this. And you'll notice now I've started building these backwards, right? I start with where we end, and then we fill everything else in front of it. Let's do it the easy way. So, okay, great. So where is it? It's on the 4th row. It's in the P block. And it's in the gallium, germanium, arsenic. It's in the 3rd column. Now, I picked this one because it makes us think here. What comes right before that? Well, that long expanse of that middle block, which is what? What orbital is that? What sublevel is that, starting with scandium and running through zinc? 3D. And how many electrons does D hold? 10. So it must be 3D10. Why must it be 3D10? Because we're beyond that. We filled it up and it kept moving. 3 more. Before 3D10, 4s2. And now let's play the game the fun way and say, okay, great. And it's got everything that argon has. Argon is its noble gas core. Which are those 18 electrons? 1s2, 2s2, 2p6, 3s2, 3p6. On the exam, on the final, I'm going to ask you to identify both full and what we call condensed or abbreviated electron configurations. Or I may just say, hey, what's the valence configuration? What's the valence? Anything beyond the last noble gas. So again, core valence. Those are filled. So there's 4p3. Arsenic will tend to do one of two things. Gain 5 or get a hold of 5 somehow, either by taking or sharing, or effectively giving up 3. It's just trying to fill or empty that last orbital. If it can get to the -5 state, then it's just like krypton. We'll find more often than not it does otherwise. Is that all right? One more. Barium, how many electrons? You should be able to count 56. 56 electrons. Who wants to write out the full configuration for barium? Yeah, me either. My hand's just up because I have to demonstrate. Where is it? What row is barium on? Row 6. Wow, what block? S block, what column of the S block? 2, 6s2. What comes right before 6s2? Xenon, warrior princess. All right, xenon. So noble gas core and 2 electrons more. If barium is going to react, and it's going to, but if it's going to, what's it most likely going to do? Try and get rid of those 2 electrons so it can just be like xenon. Why is xenon happy? Because all of its levels/sublevels are filled. What's quantum mechanics predicting then? Predicting behavior based upon configuration. If I know the configuration, I can tell you how it's going to react chemically. So after all of this mess and all of these rules and all of this other stuff, we come to rest here. Quantum mechanics has fantastic predictive abilities. Its numbers match the periodic table, which we got just from the characteristics of the elements. It explains why things in a column behave similarly because they have parallel electron configurations. And it predicts that something like barium is most likely to become barium +2, so it can be just like neon. Now let's think as well. Here's barium's nucleus. Here's 1s. Here's 2s. Here's 2p. Here's 3s. Here's 3p. There's 4s. There's 3d. There's 4p, 5s, 4d, 5p, 6s, all the way out here. Here are these two electrons, and look how far away they are from the nucleus. So just like kids at the mall, there used to be a thing called a mall. We used to be able to go there. Anyway, kids at the mall, those two kids just run off. And the nucleus is going, oh, whatever, I'll be all right. I still have 54, so I'm like neon, so I feel good about myself. We're back where we started to some extent, except now we know why. We have a theoretical reason why. So what do we know? The basic chemistries lead us back to the noble gases, the things that don't react. Things react to become like things that don't react. Quantum mechanics will tell me, okay, we could have written out all that other stuff, but this is the thing. It has two valence electrons. And the most likely thing for a metal to do, because it's simplest for this to just go, if I just lose two, I can be like a xenon. To get to the next one, radon, it's got to pick up 14f electrons, 10d electrons, and 6p electrons. Or it could give up 2. Yeah. So things are going to make their quickest trip back to the noble gas column. And that's going to tell us how it reacts. On Thursday, we're going to look at the first row of the transition metal from scandium to zinc as we fill the 3D sublevel. There's two aberrations as we make our way across. There's two times where it acts oddly. We'll explain those oddities, and then we will call electron configuration to a close. We'll then talk briefly about some periodic properties. That'll get us through chapter 8, which means we're only one chapter short of where we needed to be. If you're in my course next term, we're going to start with chapter 9. If you're in somebody else's course next term and you need someone to get you caught up on chapter 9, Ling 121T is where the old man lives, and you bring yourself in and you set yourself down and say, you were supposed to cover this last term, and now you're going to cover it with me now. And I will smile and go, yes, ma'am, or yes, sir, and we will do it. Okay? So anything next term that you think I didn't get to you well enough, come back and demand it from me. Some of you have no problems with that. Okay? And that's good. Okay? I wouldn't have done this for 30 years if I didn't enjoy it. That'd just be stupid. And I try not to be stupid, though it's within all of us to be stupid on the odd occasion. Am I correct? Unfortunately, yeah. And then we go, well, that was stupid. I'll try not to do that again, but then we probably do it at least once more just to make sure it was really stupid. I'm talking for me and not for you. In case I forget to say this Thursday, thank you. Y'all have worked so hard in trying times, and please do not think that I have not noticed it. Okay. If you would do me a great favor, you've gotten an email to do course evaluations. Do me and all of your professors a favor and take the few minutes to fill those out to give us good, honest feedback. Okay? If you fill it out and you send me notification that you have done so, I will give you one free question on the final. So it's worth something. Am I bribing you to do course evaluations? Let me say it this way. Yes. Okay? So if you could get that done, sometime send me an email, and as soon as you send me the email, what I do is I just go and I put a 4 in my little box in the spreadsheet that says extra question. Okay? Other than that, continue to watch your email and check the Moodle page, but I will be communicating almost daily from now on in the email to tell you what's coming up next. Okay? Thank you.